Hi, in this video, we want to take a look at basic regression using Keras, and we're going to be doing this inside R. All right, so Keras is a well-known machine learning neural network system, and we're going to be kicking this off using R instead of Python. Okay, so what we're going to be doing, we're going to be taking the Boston data set from the 1970s, and we're going to be using the covariates that we have to predict home value. All right, now this example is taken from tensorflow.rstudio.com. This is a really good example to dig in to get basic regression down. So definitely check that out. Okay, so first thing I need to do before I can really get going is I have to load my data. All right, so let's do that. So what I'm going to do, I'm going to use the Dataset Boston housing function from the Keras package. So remember, the Keras package in R does not use data sets. It uses special functions to give us the data. A little bit different than other aspects of R, but that's fine. Now up here, I list out the different features of the data, of the covariates. So we have crime, we have zone lots by size, we have a proportion of industry locations, dummy variable for being on the river, yes or no, the nitric oxide concentration, the average number of rooms per dwelling, age of the proportion of buildings that are occupied, distance from employment centers. This is accessibility of radial highways, and then property value tax. And this is student-teacher ratio in the town. Now here, this one, I didn't know about this one in the data set. I was surprised when I saw this, that this is based off of the proportion of Black people by town. So B is definitely like the racial aspect there. I was surprised that this was in the data set. And then we have the percentage of lower status of the population. Now, kind of an interesting field. What does that mean? But it's a covariate for our purpose, so we'll go ahead and analyze with it. Here, when we look at when we start exploring the data, we'll be able to see housing discrimination coming into play. All right, so now as I get the data, first thing I always like to do, I like to set my options for my entire workspace. Here, if I was just working on a project at work, I would not worry about these options. I would just leave, I wouldn't even make this call. The reason why I have the digits and the scientific notation modified is so that since I have an audience looking at the numbers, I don't want to have super long decimals. And I prefer to not have scientific notation to make it more easy for you to read. Now, when we look at the data set that we get from the Keras package, it's got things split up into training and test, and testing has predictors and target variable, test as predictors and target variable. All right, so I prefer to have all my data in one spot. That's just how I like to do it if I have that luxury. Well, I have that luxury because I'm just going to go do it. So one thing I'm going to do, I'm going to put all my predictor variables together in one set. I'm going to call that capital X. Now, this comes from the Keras package without column names on there. And so that kind of becomes a pain. So just to make sure I can understand what I'm looking at, I go ahead and put the column names on there. Now, the next one for my target variable, it's going to be the price of the homes, but it's going to be in thousands. And so since I want to make this a little bit easier for me to read as I look at this, as I work through, I go ahead and rescale everything by multiplying by 1,000. That way I have the actual price instead of the price in thousands. I think it's a little bit easier to read. All right, so now let's go ahead and take a look at what our predictor variables look like. So crime, And then this is zoning for lot size, industry, dummy variable for being by the river, nitrous oxide, rooms, age, distance from employment centers. This is accessibility to roads, tax, education. This one, is one where we're going to get to be able to see housing discrimination, and then lower status of the population. All right, so now let's go ahead and explore the data because I want to know what I'm working with. I want to know what I have. Okay, so what I'm going to do, I'm going to do some visualizations. So I'm going to take my data, I'm going to put it into one data frame. Now, I'm going to go a step further, and I'm going to have colors by the price range. So in my data frame, I've got my predictor variables, I've got my target variable, and now I'm going to go a step further. I'm going to get price range. I'm going to go low, medium, high. Now, initially I had 4 when I was looking at it, but I felt like 4 was too many for interpreting the graph. I feel like you could go low and high for the houses, or low, medium, high. More than that, and it gets hard to read what you're looking at. So I feel like this is probably a good way to go. So what we're going to do, we're going to do the cut function. And what this is going to do, this is going to bend the prices together into 3 different groups, low, medium, high. Now to do this, to get like relatively nice looking cutoffs and to have approximately equal size in my bins, I'm going to use the quantile function. Now you'll notice that I divide by 1,000, round it off, and then I multiply by 1,000. So what that does, it gives me like easier numbers to interpret. So this makes sure that I'm going to have zeros at the end of my cutoffs. Now, if I didn't do that, I could get some weird numbers, and this is just easier for me to look at. Now, here this prevents scientific notation. This means just write it out. I'm saying number of digits that you can write out is 22, which is the maximum that R will take. I don't know how many I need. I don't care. I just put 22. And include lowest. This, if I didn't do this, the lowest housing, the cheapest house on the market would not get put into a bin, and I'd have a missing value, and it looks ugly. So I say include the lowest, cheapest house. And now here on this step, I've got all my data in one data frame, but this is not the right format for ggplot. What I'm going to do is I'm going to go through, it's in wide format now, I'm going to take all of my covariates and my target variable, but not the bins, and I'm going to make it into long format. So it's like this. I have few rows, lots of columns. Now I'm going to have lots of rows, fewer columns. And we're going to use ggplot. So I'm going to use a histogram to look at this. All right, so there's a lot going on here. First thing I want you to recognize is that the colors correspond to our target variable. So red are cheaper homes, green are medium, and then the more expensive homes are blue. So check out price first, because price range and price correspond so nicely. So the histogram has red, green, and blue corresponding exactly how we would expect it. All right, the ones on the left are the cheapest, the ones on the right are the most expensive. And we have approximately this equal number of homes in each of the color bins. Okay, so now when I look here, when I look at age, look at the far left and look at the far right. So look at the difference between the red and the blue to see visually, is age going to be a useful predictor? Here I see when it's close to 0 age, I see that there's no red at all. When it's an older home, there's proportionally a lot of red. So I can see as age goes up, price should be going down if I have a good model. Now here, the one for that we can see like housing discrimination. Here, when we have close to a large, so it was 0.63, when we have a close to, that's probably the maximum, I'm not real sure, but here we can see that when we're close to that particular value, these are probably the black neighborhoods. Here, we can see that they are all red. They're all the cheaper homes. Okay, and so here we can see that as we deviate more from that 0.63 for the proportion of blacks, we can see that we have almost all of the medium and, or actually, well, we can say all the medium and expensive homes are on the far right. So here, I mean, this gives us a visual indication of housing discrimination. All right, so now the next one is, with regard to the river. And so it's pretty evenly distributed when it's 0. And then we can, like, it's hard to see, but proportionally there's fewer red on the river, which isn't surprising. Now, crime, we can see as crime increases, the house values go down very quickly. That is, really interesting that it just plummets so fast. So, and also the system for the histograms, there's a value over here that didn't get plotted. And so it's there, it's just hard to see that there is something with higher crime rates floating over here, or R would not have put that farther out. And so we can see that with just a small increase in crime, there is a huge plummet in home values. Now here is distance from employment center. All right, so it looks like we're seeing that there's some far distance from employment center people that are having some more expensive homes. And we can see that a lot of the cheaper homes are actually pretty close to the employment centers. Now for industry, we can see that the wealthier homes are not close to industry. And then when we have a larger, lower status population, we have cheaper homes. When we have lower lower status values, we have more expensive homes. Nitrous oxide, the greater the nitrous oxide, the less the home value. And then when we have a lower pupil teacher ratio, we have more expensive homes. And then we get around here, almost all of the cheaper homes are in this one region right there. Accessibility to highways, I'm not seeing that one separate out too much. The ones that with the greatest value looks like it does have a greater percentage of red, but it's not as distinct. For rooms, we can see that when it comes to rooms, the most expensive homes, or it's like the biggest number of rooms are corresponding to the most expensive homes. But when it's like a medium value home or a cheaper home, like there's a kind of like a range of values. So if I see a range of values on a range of the number of rooms, that can indicate it's either a cheaper home or a medium price home. And here we have tax. This one I'm surprised by, to see that much red on the right. And here is that zoning aspect. And this is for the size of the average size of the neighborhood lots. And so we can see that the larger lots are having like a lot of blue over here. And so here, these are probably the more typical homes. So if I was digging into this more, I would explore converting this one into a binary, where it basically just overcut. If it's over a threshold, it's 1, below a threshold, it's 0 for this, because of how lopsided this is. Also, I would consider that for RAD. All right, and we can do the same thing with box plots. So box plots, what I'm looking for is I want to see the box like this. If I see a difference, that gives me an indication I have a good solid predictor. So age, I can see that age is good for distinguishing cheap versus not cheap, because the green and blue are parallel with each other. The red is above. So age is good really for distinguishing between the less expensive homes and the medium or expensive homes. here we can see that the cheaper homes have a far more range for the Black community. Then the dummy variable, it's squeezed out so much it's hard to tell what's going on. It's a binary vector, so there's not really a whole lot we can do. That we can just tell that there aren't that many on the river. So crime, we can see that crime corresponds strongly with cheaper homes. And then distance from employment, definitely see that distance is good for distinguishing between cheaper homes, but it doesn't really help for medium and expensive homes. And for industry, I'm interpreting this as it's good at it's good at separating the expensive homes from the not expensive homes, since the red and the green have box plots looking like this. The lower status is going to be good for distinguishing between all three levels. Nitrous oxide, yeah, I think this is lower price homes versus non-lower price homes is probably the utility of this one. Price is not useful on the box plots as a predictor, right? Because it's our target variable. And then, pupil-teacher ratio. Here, I interpret this as pupil-teacher ratio is good at distinguishing between the cheap homes and the not cheap homes, because this box plot is higher than these two. And I see that the lines are pretty close to just being like this. It's not cool. There is a little bit of a difference, but not a lot. And we can see a pretty big difference on the median, but they're, kind of a wide interquartile range, definitely a skewed distribution when it comes to the lower price homes for access to roads. Number of rooms, we can see that the lower and medium price homes are parallel to each other, but the expensive homes are higher up. And so because of that, I conclude that rooms is better at detecting expensive versus not expensive. And then tax does a good job of distinguishing between the cheaper homes and the not cheaper homes. And then the zones is useful for distinguishing between the expensive homes and the not expensive homes. All right, so something I always do, I like to use single linkage to check for outliers. Basically, the idea here is if I do clustering and an observation is by itself, then probably it's an outlier. Because if it's in its own cluster, then it's far off from everybody else in a multidimensional sense, and then I'm concerned about being an outlier. All right, here in single linkage is, in my opinion, the best way to go for this. Complete linkage and wards D have other utilities. Complete linkage is better for interpretation. Wards D is better if I want relatively even cluster size. So what I'm looking for observations that are by themselves. And so possibly this one here is a concern. But it's really not that far off compared to the rest. But if I was going to be digging more into this, I'm kind of just doing this quick. But this is something you should always do when you're doing your real life data mine. This observation that corresponds to that leaf, I would want to pull out. And now I can plot. Something else I noticed is that really we have like two clusters of data going on by this model. And so I went ahead and did a principal component plot of the first and second principal components. Actually, let me scroll up just to show you how I'm going about this. All right, so I am doing principal component analysis. I'm only grabbing the first two principal components, and then I am using the cut function, same cut I had before, but this time I'm labeling it as red, green, and blue, same way as I had previously using ggplot, but here I have to say as dot character, otherwise it's going to give me a factor and it's going to look screwed up. And so here I can see that this is like one cluster, And this is another cluster. All right, this cluster over here is going to be the cheaper homes, but there are some blue and greens in there, right? So this, principal components, first two at least, are not fully separating out the data. And then over here, this cluster has more expensive and medium price homes and proportionally fewer cheaper homes. So this guy just says, the first two principal components are not sufficient for getting a good separation at this point. All right, something I like to do whenever I'm dealing with my data is I like to kind of mute out large values in my predictors. All right, when I'm fitting my model, everything is about like leverage and optimization. So if I have a large value and I'm squaring something, anytime I have a large value and I square it, it gets a heck of a lot bigger. All right, why is this important? When we talk about mean squared error, squared, if I have a larger error, it inflates a lot when I square it. Okay, that means that the algorithm, to a large extent, it's more concerned about avoiding big values than it is about just kind of getting like good overall fit. So because of that, I like to just kind of mute down, trim down my more extreme values whenever I do my model fitting. So what I'm doing here, I'm taking my 95% quantile interval. All right, so I take the quantile for 0.25, and I take the quantile for 97.5, and any values that are outside, I just kind of reduce them down just to those boundary values. And what that does, that helps make sure that I don't have any like large leverage points in my predictor variables, and I don't have the opportunity for my mean squared error getting pulled off. So if I have a large value in my y value, in my target variable, that model is going, if I'm using mean squared error, that squaring aspect is going to try and fight like heck to try to not have a large value, because when I square it, it gets even freaking bigger. So muting this down, in my experience, improves model performance in the actual results. Now, I will be not getting like the best fit possible on my data, but remember, my goal is not to get the best fit on my data. My goal is to get the best fit on the data I haven't seen yet. Okay, so my model is all about predicting in the future. I need the best model for what's going to happen in the future. The outliers I have are not good representations of the future values. All right, so now in this next step, I'm going to normalize my data. I'm going to divide by, for all of my predictor variables, I'm going to subtract the mean, divide by the standard deviation. This is a standard process. Anytime I'm building a model, anytime I'm working with something where standard deviation influences outcomes, where frequently standard deviation can be interpreted as a weight in an algorithm for a particular variable. If I don't want that weight, if I want everything to have equal voice, equal weight in the system, then I need to do something to deal with it. And so the Keras package gives us two options. Either I can rescale the values so that they go from, let's say, 0 to 1, or I can normalize. The example on the website is to normalize. I feel like normalization is a good choice in almost all cases. So that's what we're going to do. All right, so what we're going to do, we're going to use the Regression package because I want to be able to do piping. All right, so you'll notice I've got pipe operator and I've got pipe operator. I'm going to be going pretty heavy on the piping for the rest of this. The feature specification, what this function does, this is in the TF datasets package, this specifies which variables I'm interested in working with. And then step numeric columns, I'm going to take all numeric, and then I'm going to do a scalar standardization. So this function, if I use this one, subtracts the mean divided by the standard deviation of all of the numeric variables I pass to it. This function grabs all numeric variables in my data set that are predictor variables. And then I pipe it to the fit function. Okay, so this specifies the features that I'm going to be working on. This specifies, or this part specifies which columns are going to be grabbed, going to be worked with, and then this specifies how they're going to be manipulated. And then this step right here goes through and actually does the rescaling for us. Okay, and so when I do this, I get feature specification. So I'm doing feature engineering on 13 predictor variables. And we have these 13 being manipulated. You notice that price is not in there. All right, so this is not changing my target variable. All right, now I'm going to create a dense tensor layer. Okay, so here, what I'm doing is I'm going to take, I want to create a dense tensor layer using the features. All right, so what I'm doing is the dense features. I'm taking the output from my data manipulation up here. So I'm taking I'm taking these values, and we're going to define a dense feature off of them. And here I'm specifying what is my data type. All right, so remember in R really doesn't have a lot of data types compared to other languages. Python has more. Because of that aspect, we have to be a little bit more specific. And so the TF object in the TF datasets package, we just specify float 32. And by specifying this, I'm telling the Keras system, which is actually under the hood. It's not actually using R, it's using C++ under the hood that we don't see, to give us things in terms of what Python likes for float 32. And so my output, I can see that this is TensorFlow, Python, Keras, feature column, dense features, V2, and then just the dense features off of the object. And so if I go ahead and pass my data set in there, we can see that it goes through and puts this into a Python format for us. And so we have our data is all like set up in the right way. Okay, so now what we want to do, we want to go through and we want to get an input layer. This is our data layer inside our model. All right, so what we've got going on, our model is complicated enough that we have different aspects, different components to it, and I'm building each component individually. Then I'm going to put them all into the model fitting soup at the same time. And so I'm using the layer input from dataset function. So this is input layer. This is the TF datasets. I specify the data that I want. So you'll notice I'm taking my data, but I'm pulling out the target variable. The dplyr statement of select, you'll notice I have negative price. This is pull out my target variable. Remember that this data set doesn't have those bins with it. The bins were only in the data set I use for visualization. And so we can see that the layer has 13 items in there. All right, now let's go ahead and create our output layer. All right, so in our output layer, what we're going to do, we're going to pass our input layer using piping. We're going to put that into the dense layer features. Here we're specifying which features to be working with, which are the features that we specified in the data prep step. All right, so here I'm saying this is what's going to be passed into the system. This is the first dense layer of nodes. We've got 64 of them. We're using ReLU activation function. Now we've got exactly the same thing going on. We're going 64 units. We're using the same activation function. And then I'm saying I want one dense layer of one item. Okay, so why is it there just one? Because I have one target variable, price. And so I can look at my outputs and we can see that we have a Keras tensor. Type specification is a tensor spec. Here's shape in a Python format. Data type, once again, Python name is equal to none because it wasn't specified. And then, other aspects. All right, so now what I've done, I've set up what are my actual inputs and outputs. Now this isn't quite enough. What I need to do now, I need to actually get my model going. So I want to define what is my model structure. All right, so what I'm going to do, I'm going to take the Keras model function from Keras. I'm going to specify what is the input. So this is my prepared data, my normalized data. I'm going to specify my output, which we did just a moment ago, which included using the inputs, by the way. And so here, this is enough to define what the model structure is. Now, there's a little bit more though. Now, the next part is split up in the original tutorial. I went ahead and put them together. That way I have fewer steps. This step here, the compile function, what it does, I'm going to specify mean squared error for my loss function. I'm going to specify my optimizer, root mean squared, and then proportion. And then my metric, my method of actually measuring the mean absolute error, that is going to be my way of evaluating model quality when I do my validation step. And so now I want to take a look and see what do I have. Okay, so my model, I've got all my predictor variables going in. We can see that they're all here, going from age to zoning. Now there's no, the output shape is not an issue here. No parameters because these are my inputs. Now I've got my dense features. All right, so this is specifying the variables that are going in. And then I have my first layer where my first dense layer that is like the actual neural network part. I've got 64 going on. All right, now here's the number of parameters. You'll notice that this is actually more data than I have. All right, anytime your parameters exceeds the number of observations you have, know that you're in like dangerous waters. But for this one, this is okay. Because the model structure and the data match up. If we have more parameters than I have observations and data and model structure don't match up, I'm going to get smacked in the face with bad predictions. And here is the dense features. This is part of the connected to aspect. All right, so here what this is saying is that our predictor variables are connecting to dense features 1, and then dense features 1 is connecting to dense 2, like that. And then dense 1 is connecting to dense 2. And you can see we have even more parameters. And so this is corresponding. So here we're going from 64 to 64, or no, yeah, something like that. And then we are going to from dense 1, we go to dense where I have just one, one thing going, because that's going to correspond to our target variable. So we can see we have over 5,000 parameters. That's a lot, especially for this data set size. All right, so now let's actually fit the model. Okay, so what I'm going to do is I'm going to use the fit function in the Keras package. I'm going to specify my predictor variables. Notice that the negative price inside select specifies drop price, drop the target variable from this data set. And then here's my target variable. Here's the number of iterations we're going to go through. I like to do 50-50 validation split. If you can't get a good model off a 50-50 validation split, you're probably not going to have a good model when you actually launch it. So by pulling back some of my data, my experience is that I have a better indication of how things will actually perform in the future. And then verbose equals 0 means don't print anything. If verbose equals 2, it's going to print stuff for every single iteration. There's 500 of them. It's going to be a lot. I don't want to deal with it. All right, so let's look at what we get. All right, so for our loss function, which was mean squared error, we can see that it gets going. And then look at the teal. That's our validation. That's the one we really care about. It gets going, and then all of a sudden it plummets, and then it flattens out. I don't really get much improvement. And for mean absolute error, I have the same pattern. It goes down. Now, something that is always important, if I see a deviation between my training and validation, the bigger the deviation, it's an indication I'm overfitting. I don't see that. These are staying relatively parallel to each other. You know, of course, I would like these values to be smaller, but it is what it is. All right, so now something that I do when I'm working professionally with data is I do not leave data on the table. My validation split, I was not using all of my data to train it. So, all right, so what I was doing there, I was training my model, and then I was validating on data that had not been seen yet. All right, that's standard practice. Now, if I was just to go with the data that was fit and then just go and proceed and do stuff, then I would be not using any of this for the actual fitting process. Now, if I was to go, let's say, you know, a train validation split of 70-30, 70%, 30%, then it wouldn't be as bad as 50-50, but I'm still leaving data on the table. I could go with 0.9 and 0.1, right? All right, 90-10, that, you know, that would be good, but then I feel like 10% isn't really enough to get a full impression of your validation statistic. So I like 50-50, splitting your data in half. You'll find speeds up computations by a lot in a lot of situations. And so for model exploration, I feel like it's a good choice. But then when I go through and I actually pick the model I'm going to use, I go through and I refit the entire model using the entire data set. All right, this way going forward, I have, you know, this is what I believe the best possible model I can get. I'm not leaving anything hanging back. All right, so I'm doing the same exact thing I did before, but my validation split is 0. I'm saying put 100% of the data in training. Don't worry about validation. Now, a lot of people don't like this. They feel like this is modeling blindly. They're right. But you know what? I'm making predictions. I don't actually know what's going to happen anyway. You know, you don't know if you have a good model until it's too late. All right. So what you have to do when you look at this model and you evaluate it, you have to know this is optimistic. Everything you're looking at is an optimistic value. As long as you keep that in your head, you should be okay. Now, I want to point out, look at what I get for my mean absolute error and my loss, my mean squared error. When I look at this, I've got substantially smaller values. I was really surprised by this. I didn't expect this. All right, this value here is 10,000. 10,000 isn't even on this scale. And that's on, you know, 10,000 up here is after, you know, about 150 iterations. Now, so we are definitely getting a better fit to our overall data. I'm using 100% of my data. So I feel like this really is a better way to go. Now, remember, this is optimistic. This is a training statistic. This is not a validation statistic. This is not a test statistic. This is running, this is the error on the data that the model was fitted on. All right, this is optimistic. These numbers look better than what is going to happen in the future, but I still feel like this is the better model to work with. So I will proceed with it. All right, so now let's check out the training statistics. Once again, remember, training statistics are always optimistic. I don't trust these to be the actual values I get, but these just give me some feedback on what's going on. All right, so I'm going to use the evaluate function inside Keras. Once again, I'm giving my predictor variables, I'm giving my target variable, and I'm saying don't give me a lot of information on the iterations, I just want the output. And so here, remember, this is the mean squared error. And when I'm talking about squaring, 1, 2, 3, 4, 5, 6. All right, so this is, if I was to do like the square root, I would be, reducing this down to like 3. So this would be, a much smaller value. Like the digits would be something like that in size, digits wise. So that's going to be around maybe 30, or sorry, about 3,000, something like that. All right, and now my mean absolute error is, a little bit over 2,000. All right, so these are optimistic values, but these are numbers that if I'm using mean absolute error, that's a number that's easier to interpret. When I talk to a stakeholder, if I'm talking about mean squared error, they don't know what's going on with that. They don't understand it. They don't know why it is that's so important. Mean squared error is super important, for those of us who do hypothesis testing and do regression and do stuff like that. To everybody else, if you're not a statistician, if you're not worried about ANOVA and maximum likelihood error, stuff like that, mean squared error is meaningless to you. Mean absolute error is easier for stakeholders and decision makers to work with. All right, so now what I want to do, I want to go ahead, I want to compare the predicted values on my training data. So remember, this is optimistic, my training data compared to the actual target variable. And so once again, I'm going to get my predictions. I'm going to get my data frame. I'm going to do the same system for coloring the points. And then I'm going to look at the plot using ggplot, and I'm going to look at the residuals. Okay, so here I have the predicted price. Down here I have the actual price. And I can see it's not a perfect model, but is it reasonable? Yeah, I think so. It's not horribly off. And here are my residuals. So something I want to see in my residuals is I don't want to see a trend. If I see a trend in my residuals, that is really like a space, a region in my data that my model is not performing well for. And I would have to start diagnosing and digging in. All right, well, I'm satisfied with this model, and that's all I got for you. Take care and goodbye.